Greetings for the day. I'm Dr. Sunita Singh, presently working as Assistant Professor in Department of Chemistry, Navikanya Mahavidyalaya, Lucknow. It is a pleasure for me to be part of this PM USHA program in which Shivaji University is running an value-added course on scientific tools for research in chemical sciences, which is basically for MSc second year students. As we know that after PG, we usually go to the uh, uh, different fields in which research is also one of the important area, and people used to carry PhD as a highest degree for their future endeavors. So for me, it is a very interesting topic to discuss because I also did a PhD on essential oils, where different types of characterization techniques and other investigation studies are needed. And there is a very drastic shift when we go from our PG courses to research area. There are different studies, and there are different synthetic applications, synthetic routes for different compounds. And for confirming these compounds, either it is inorganic or organic synthesis, we have to confirm these compounds or confirm these products through different techniques. Like if we synthesize any compound, we have to confirm that it has a particular structure um, through various studies like IR spectroscopy, we have UV spectroscopy, and other spectral studies help us to determine the structure of that compound. And there are also studies related to kinetics, as well as for inorganic compounds, we have different types of estimations. So everything is very interconnected. You can't say that I'm doing my research in physical area or organic area, so it is limited to that area. There is a combination of all areas like organic, physical, and inorganic to complete our research, we can say research objective. So that's why I have chosen this principles of IR spectroscopy, although it is a very vast topic and we can't learn everything in one lecture, but I have tried to give a gist. At least when you go from MSc to your research, you should know how IR spectroscopy going to help you for its use. Like like IR spectroscopy can be used for determining the functional groups, what are the IR, how this IR spectra looks like, and what are the instrument we use in IR spectroscopy. So in this lecture, we are going to cover points like introduction, fundamental modes of vibrations, factors affecting vibration, sample handling, instrumentation, and its applications. As I have earlier told that it is very difficult for compile everything in one lecture, but I have tried. At least you can get a gist, as well as it's how it is going to be applied in different areas. Spectroscopy means a method which is for seeing the unseeable, which we can't see directly. So for that purpose, we utilize this spectroscopic. We have different types of spectroscopic like UV spectroscopy, IR, NMR, and they usually use electromagnetic radiations to obtain information about atoms and molecules that are too small to see. IR spectroscopy is the study of absorption of IR radiation, which results in vibrational transitions. Actually, in different spectroscopy, you see like there are different factors which arise, which are responsible for creating such type of spectra or creating frequency. So in this IR spectroscopy, the vibrational transitions are the main factor responsible for IR spectra. They are mainly used in structural elucidation to determine the functional groups. They are present between, this IR region is present between visible and microwave region in electromagnetic spectrum. And they are further divided into three regions that are near IR, middle IR, and far IR. you can see in this slide that this IR region is between visible and microwave. So it is this is, topic is also important for your net preparation also if you are going to pursue research after PG. So these topics are very important, and you get a question in which this whole data comes to compare to elucidate any compound. Like you have IR data also, UV, mass spectrum, and you have to apply all the concepts to get the answer. So every spectroscopy which are defined in your assignment or in your syllabus is very important, and I'm very happy that your university has taken this initiative to run this value added course on a very important topic, because when we shift our journey from PG students to research field, everything looks very new, and we are very in a confused state. We don't know how to proceed further. So if we have little bit knowledge about different type of studies, and how this research area explore our different techniques, so it would be very useful as well as helpful to any researcher. So I congratulate the whole team of this value added course who tried this new thing, because and it is also very important for NAC purpose also, and value added courses are getting extra credits for this, and very relevant topic. It means like we should know, and it is not specific to any chemistry field. I think this type of courses are applicable for other subjects also. The infrared region in electromagnetic spectrum is divided, as I have already told. Far infrared, which is lies between 400 to 10 centimeter inverse. Mid infrared spectra, mid infrared 4,000 to 400, and the near infrared 14,000 to 400. So the basic which we usually use is the mid infrared region. Which is used to study the fundamental vibrations and associated rotational vibration structure. The near infrared region has higher energy and can excite overtone and harmonic vibrations. Whereas the far infrared lies adjacent to the microwave region and has low energy and used for rotational spectroscopy. This is the wavelength in centimeter, micrometer, and in wave number also, and the energy associated with these regions. The basic principle lies in IR spectroscopy is that the study of interaction of electromagnetic radiation with vibrational and rotational references with a molecular structure is termed as IR spectroscopy. So here, when energy in the form of infrared radiation is applied, then it causes the vibrations between the atoms of the molecule. So the vibrations are responsible for the spectra. When IR frequency is equal to the natural frequency of vibration, absorption of IR radiation takes place and a peak is observed. So natural frequency is equal to that amount of IR frequency that we have applied to that atom. And IR spectrum of a chemical substance is the fingerprint of a molecule for its identification. Yeah, the term fingerprint is used because it is unique for everyone. My fingerprint can't be similar to your fingerprint. So this IR spectrum gives a fingerprint of that molecule. It means it will help in to differentiate from the other molecule. It is a particular unique spectra of the given molecule or the given compound. The vibration frequency in the two atomic system containing mass m1 and m2 is related to the force constant, and we have Hooke's law, and we get this equation where nu bar is equal to 1 upon 2 pi is under root k upon mu, where k is force constant, mu is your reduced mass. So this formula also help us to know that the larger the force constant of the bond between two atoms, higher is the vibrational frequency. So you should know, like the compounds containing double or triple bond, they have higher vibrational frequency in comparison to single bond, because their force constant is higher than the compound containing single bond. There are typical requirements that are needed for IR spectroscopy. A molecule to absorb IR radiation, the natural frequency of vibrations of some part of a molecule is same as the frequency of incident radiation. So correct wavelength of radiation is needed. And second one is the change in dipole moment. uh, uh, if a molecule has a similar same dipole moment like N2 molecule or H2 molecule where there is no change in dipole moment, so they are IR inactive. But a molecule can only absorb IR radiation when its absorption causes a change in its electric dipole. A molecule is said to be electric dipole. You should know like dipole is the separation of positive and negative charge. And we have a slight positive and slight negative charge on its components of atoms. So these are the basic conditions. So you can also go if you see a molecule where there is a chance of a change of dipole moment, you have an idea like they are going to be IR active compounds. There are different types of vibrations which are found in the compound. They are basically divided into, we can say, two types, which are further divided into various different class, like stretching frequency, stretching vibrations, which are further divided into symmetric and asymmetric. Bending are further divided into in-plane bending and off-plane bending, out-of-plane bending. In-plane bending is scissoring and rocking. Out-of-plane bending contains wagging and twisting. So these are different types of vibrations, and these vibrations give different frequencies. We can't say that the frequency of symmetric and asymmetric will be going to be same, or the in-plane bending or out-of-plane bending is same. So these are the different types of vibrations that occur in a molecule. Here you can see a picture which shows symmetric stretching, asymmetric stretching, symmetric bending in a plane, symmetric bending out of plane, and asymmetric bending and asymmetric bending vibration out of plane. So the arrow shows how the atoms are going to move. Like in symmetric stretching, both atoms are going on the similar distance from the center molecule. And in the similar way, asymmetric stretching in which one is going to the other side. They are working in two different directions. And I have tried to give up, I have found a video which will clear your concept about different type of stretching. You can see how this symmetric stretching, anti-symmetric stretching, scissoring, rocking, wagging, twisting is working. There are various factors which affect the vibrational frequencies. Yeah. Before going to the spectra part, we should know how these factors work, because we should know that if a compound having a hydrogen bonding, if there is a strain in the molecule, is the resonance play a vital role in determining the vibration frequency. So these are very important. So vibrational coupling, hydrogen bonding, electronic effect, bond angles, and resonance are the major factors which affects the vibrational frequency, because it is all about vibrational frequency, how these vibrational frequencies are going to work. Like these are these factors are going to affect, or the vibration frequency is going to remain the same. Vibrational coupling. If we have an isolated CH bond, I'm taking an example, it has only one stretching vibration frequency, whereas methylene group shows two stretching frequencies, symmetrical and asymmetrical. Because of coupling or interaction between CH stretching vibrations in the CH2 group, and it is also found that this type of coupling affects the vibration frequency, and the asymmetric vibrations always occur at higher frequency. So we should learn, or we should have an idea about that asymmetric stretching has higher frequency in comparison to the symmetric stretching vibration. These they are known as vibration coupling, because these vibrations occur at different frequencies than that required for an isolated CH stretching frequency. So the isolated CH frequency is different whereas the CH2 frequency has different, we can say the magnitude is different because it has symmetrical and asymmetrical stretching, and in which asymmetrical stretching always occurs at higher frequency. Hydrogen bond. It is also an important factor because we know that hydrogen bonding is especially occur in OH and NH compounds, give rise to a number of effects in infrared spectra. While although the most of the work, this IR spectra work is involve non-associating solvents like CCl4, carbon tetrachloride, carbon disulfide, chloroform, but more solvents such as acetone or benzene will certainly influence OH and NH absorption. So there, where there is a chance of hydrogen bonding, there if they these effects are shown in the spectra also. Like the NH frequencies of amines are also affected by hydrogen bonding, but the shifts are more prominent in the case of OH bonds, where OH are involved. Like it is found that where there is a intermolecular hydrogen bondings, we have broad bands. Broad bands means we can see similar. We can see the bands are little bit far or a little bit clear, whereas in intramolecular hydrogen bonding, sharp bands are found. You can see the peak are very sharp in that case. So the sharp peaks are also depicts that there is an intramolecular hydrogen bonding involved. Electronic effects also, like changes in the absorption frequencies for a particular group take place when the substituents of that group are changed, like inductive effect, mesomeric effect, field effect. All these effects play a very vital role when it comes to vibrational frequency. Like in acetone, like for an example, we have taken acetone and chloroacetone, where acetone we have 1715 centimeter inverse vibrational frequency, whereas in chloroacetone we have 1725 centimeter inverse vibration frequency. So it can be seen that the plus minus I groups increases the vibration frequencies, whereas plus I groups decreases the vibration frequency. In acetophenone as well as in we have para-aminoacetophenone, we can see that para-aminoacetophenone somewhere decreases the we can say plus M effect decreases the vibration frequency, whereas in acetophenone there is no such type of effect is shown. So the frequencies comes at the higher end, which is 1693 centimeter inverse. So for a you have to see the whole environment of that compound. Like, is there any type of hydrogen bonding? Is there any type of vibrational coupling? Is there any electronic effects that are going to play for depicting the vibrational frequency? Bond angles. CH is stretching frequency vibrations move to higher frequency in the sequence alkane, alkene, and alkyne. As hybridization goes from sp3 to sp to sp, the S character increases, bond length becomes shorter, and the frequency rises. As we have also learned in the particular Hooke's law equation, that force constant is higher, the vibration frequency is going to be higher. In this case, bond angles like where there is a very strained molecule, like when we have cyclopropanone, cyclobutanone, and we have cyclopentanone, cyclohexanone. This one is a normal, we can say a ketonic group. So we can see as the strain in the molecule increases, the frequency also increases. Cyclopropanes have high CH stretching frequencies for the same reason, because the bond angle is below the normal 109.5 degree, which is leading to increased S character and thus to higher frequency. So it can be seen that how these bond angle strain play a vital role when it comes to the vibrational frequencies. Resonance, because of the resonance also play an important role. Resonance carboxylic acids show more absorption compared to alcohols due to the resonance bond strength increases and results increase in the absorption of frequency. And in the same way, it can affect the absorption of CO stretching. So resonances also play an important role when it comes to the magnitude of the vibrational frequency. Now it's come a important part, instrumentation part. Although this instrumentation part will be more clear when we see the instrument, and I have at least give you a rough idea about how this instrumentation works. And I hope, or I hope, like you have this type of instrument in your university, because our college don't have such type of instrument. So because if what we see, we capture or we catch these things very easily. So the instrumentation part is basically divided into source, sample, monochromator, detector, and readout, where different type of sources, monochromators, sample cells, and detectors are used in IR spectroscopy. There are different sources. The radiation source must emit IR radiation, which must be intense enough for detection, steady, extend over the desired wavelength. So these are some of the basic conditions for have a radiation source in IR spectroscopy. The popular sources of IR radiations are a nurse glower, global source, mercury arc, and incandescent lamp. These are the radiation sources which are commonly used in IR spectroscopy: nurse glower, heated rare earth oxide rod, global heated silicon carbide rod, tungsten filament lamp, mercury arc lamp. So these are some of the radiation sources in IR spectroscopy. Monochromatous, which is used as a dispersive element constructed of various metal halide salts. Sodium chloride is the most commonly prism salt used. So this monochromatous act as an dispersive element. And we have grating. Gratings are nothing but they are made up of materials like glass, quartz, or alkyl halides, and they help in the mechanism is that diffraction produces reinforcement, and the rays which are incident upon the gratings gets reinforced with the reflected rays. Samples and sampling of substance like infrared spectra may be obtained for gases, liquids, or solids. Materials containing sample must be transparent to the IR radiation. This it is an important condition. So salts like NaCl, KBr are only used. You can see KBr, pellet, pressed, liquid cell, and other pestle mortar is used. uh, Sample handling. We have different techniques for different techniques or different handling methods for solid, liquid, and gases. For solid, we have solid run-in solution, mull technique, pressed pallet technique, and solid films. Like samples of the same substance show shift in absorption band as we pass from solid to gases, and hence the samples of different phases have to be treated differently in IR spectroscopy. So for sampling of solids, we have solids run-in solution, mull technique. In solids run-in solution, we dissolve the desired solid sample in non-aqueous solvent and place a drop of this solution in alkali metal disc and allow to evaporate, leaving a thin film which is then mounted on a spectrometer. Mull technique, finely powdered cell, is added with mulling agent like Nuzol and make a thick paste, transfer the mull to the plates, and the plates are squeezed together to adjust the thickness. It is then mounted in spectrometer. In pressed pallet technique, final powdered sample is mixed with KBr and in a vibrating ball mill, and the mixture is then pressed under very high pressure to give a small pellet. And in the solid films, where amorphous solid is dissolved in volatile solvents and this solution is poured on a rock salt plate, then the solvent is evaporated by a gentle heating. So these are the commonly used method for the solid compound, solid substance which are going for IR spectroscopy. For liquids, liquid samples can be sandwiched between two alkali halide plates. The sample thickness is around 0.01 to 0.05 millimeter. And for sampling of gases, gases sample is introduced into a glass cell made up of NaCl. Very few organic compounds can be examined as gases. Okay. So these are some of the common methods how the samples are handled when it comes to their different phases. Like we have in the block diagram, we have shown that detectors are used. So there are different types of detectors, of thermal, pyroelectric, and photoconducting detectors, in which detectors like thermocouple, bolometer, Bole cell, pyroelectric, and photoconductive cells are used. And they have different advantages, like thermocouple are cheap, bolometers are highly sensitive, Golgi cells are faster than others and having wide range of wavelength range, pyroelectric fast and as well as sensitive. In photoconductive, we have fast and sensitive results when it comes to photoconductive detectors. These dispersive IR instruments are introduced in 1940s and double beam instruments are mostly used than a single beam instrument. In dispersive IR, sequential scanning of wave numbers of light takes place. So, as I have already told you that this type of instrumentation is difficult to analyze when it comes to showing through the slides, and it is very important attend. I suggest, like, if you get a chance to have hands-on training or workshop on these type of instrument, you must attend and know how these instruments work. Because in PhD also sometimes we have different types of collaborations and we send our samples and we get a result, but we don't know how these instruments used to work. So I suggest or I request all of you to please attend any type of hands-on training or workshop on these type of topics which are related to these different analytical techniques which are going to be very vital in your research. This is one more FTIR instrument. It collects all wavelengths simultaneously and at once, and it works on Michelson interferometer, which having beam splitter, fixed mirror, and movable mirror. So basically, I want to give an idea about the instrumentation. I am sure, like I know that it is very difficult to analyze these instruments through these slides, but still, at least you know how these instruments work. The typical the typical IR absorption range for covalent bonds look like this. The graph shows the regions of a spectrum where the following types of bonds normally absorb. We have different, we can say different frequencies for different functional groups, like for NH bond, for OH bond, for CH bond, CH having symmetric as well as asymmetric stretching. This fingerprint region also. So this is a particular graph between percentage transmittance as well as the vibrational frequencies. This is the spectra, how it looks like. Like we have sharp peaks as well as broadened peaks. This you can see the single bond stretch in green, triple bonds in blue, double bonds in yellow, and fingerprint region skeletal vibrations in pink. The fingerprint region, although the entire IR spectra can be used as a fingerprint for the purposes of comparing molecules from 600 to 1400 centimeter inverse. This range is called the fingerprint region, and it is normally a complex area, and the focus of your analysis on the region which is beyond, which is on the left of that 1400 centimeters. 600 to 1400 is the fingerprint region, and it is difficult to interpret reliably, and but our focus is on the this part which is left of that 1400 centimeters. Fingerprint region is a little bit complex area. Applications of IR spectroscopy, which is one of the important part of this lecture. Identification of an organic compound. No two samples will have identical IR spectra, that I have already told about it is a fingerprint of that compound. We have different frequencies for the different functional groups. This is a typical table in which we have different, we have wave numbers for groups like C double bond. If we have C triple bond N, we have a wave number in between 2260 to 2220. We have for OH, we have 3300 to 2500. If it is a carboxylic acid OH, if it is a alcoholic OH, it is around 3650 to 3200. So the presence or absence of absorption bands help in predicting the presence of a certain functional group in the compound. So at least we have a rough idea about these frequencies when it comes to solving any problems related to IR frequency. This is a diagnostic region for single bonds as well as double bonds. We have different frequencies. It can quantitative analysis. It can be done by measuring the intensity of the absorption bonds. So application involves this also, and it is also helpful in identifying the impurities in a drug sample. Like impurities have different chemical nature when compared to the pure drug. Hence, these impurities give rise to additional peaks than that of a pure drug. This is one of the spectra of methanol. In which we have different vibrations like OH vibrations, CH vibrations, CO vibrations also. And OH vibrations is also affected by the hydrogen bonding, because we know that in methanol molecules, hydrogen bonding also occurs. The absorption band is broadened by intermolecular hydrogen bonding, which I have already told in the factors affecting the vibrational frequencies. Okay. This is the acetic acid IR spectra, where we can see there is a OH bond in a carboxylic acid has a different frequency. CO bond is also present. C double bond as well as CO bond is there. So these wave numbers also depicts the different bonds present in that compound. There are, although we have learned very good things about IR spectroscopy, but there are still limitations. By IR spectroscopy, it is not possible to know the molecular weight of a substance. It does not provide information of the relative positions of different functional groups on a molecule. From a single IR spectrum of an unknown substance, it is not possible to know whether it is a pure compound or a mixture of compounds. So there are some limitations of IR spectroscopy. That's why we have to go for other additions. Like we have to confirm any type of compound through IR, UV, we have mass spectra and other spectral techniques to confirm that compound. IR spectroscopy if we say individually can't confirm that compound. So this is a gist of my lecture on the topic of principles of IR spectroscopy. Sorry for some technical glitch, as well as I have a daughter 3 years old, which is disturbing me a little bit. So I hope I have given you an idea and a concept about this IR spectroscopy. And thank you so much to the organizers, especially Tayade sir, for giving me this opportunity to be part of this PM USHA initiative and this value-added course. And best wishes from my side to this value-added course who are attending this value-added course. I am sure that you are going to be very benefited from this whole course, and it would be very helpful in your research endeavors. So these are my sources from which I have made this presentations. And thank you so much for your time. And sorry that I am not able to present live with all of you due to some commitments, because as you know that earlier we have holy celebrations, so we have some other commitments to fulfill that one. So once again, thank you so much for your time. And if you have any type of query, sir has my number and email. So you can just give me a message or mail. I will try to solve your queries. Thank you so much.